okay, which is 1 10 to the power minus 3 dt, and substitute, you will get this value. You see this value. Now minus, okay, we integrate this again, it is multiplied by time, substitute for this value and t, then we go, the final formula is this one. Now I have two formula for the time from 0 to 2 and from 2 to 4 millisecond. I can write the formula. Now if I have the charge, you remember Q equals CV, so V equals Q over C. I have a Q, just divide by C. Very easy, straightforward. For the two parts of the formula, from 0 to 2 or from 2 to 4. You can see here, this is the first part, the second part. I have voltage, I have current, also multiply them to find the power, as you can see here. From where to where? From 0 to 2, from 2 to 4. Please, I advise you to do it by pen at home. Try to do it. Check it how you got with this. We come up with these numbers. Now for energy, we have the power. Just integrate again from 0 to 2, from 2 to 4. Integrate these parts. Integrate this part first, and then integrate this part second. Now, what about connecting capacitances in parallel and series? In parallel, as you can see here, the voltage across them is the same, okay, the same voltage. So if I represent the current following in each one of them and then use Kirchhoff current law, then I can find the equivalent capacitance. See here, current I following I1 equals C1 dV over dt for the capacitor 1, and 2I2 C2 dV over dt for capacitor 2, and the same thing for capacitor 3. If we calculate input current to the node, this is the node voltage, you remember? Kirchhoff say the current entering, all the currents entering the node equal to all currents coming out from the node. So I will be I1 plus I2 plus I3. If I substitute the first capacitor current, the second capacitor, the third capacitor, and considering that the voltage is the same because they are connected in parallel, so I can't take it as a common factor. You see here? Then this C1, C2, C3, we add them together, represent C equivalent. Okay, if I cancel this part with this part, what we can C equivalent equals C1, 2, 3. So this tells me that when we connect capacitances in parallel, we add the capacitance to come up with the equivalent capacitor. It's different from connecting resistances in parallel. This is equivalent to connecting resistances in series. You remember we add them. For capacitors, they are connected in parallel. No, we add them in parallel, not in series. Now next is capacitances in series. You can see here. Now I will use also Kirchhoff voltage law, because what Kirchhoff say? The voltage here of the circuit equal voltage across the capacitor 1 plus capacitor 2 plus capacitor 3, because they are connected in series, as you can see here. And you remember that to find the voltage for the capacitor, 1 over C integration current with respect to time, as you can see here, for capacitor 1, for capacitor 2, for capacitor 3. But just a minute, they are connected in series, so the current will follow, is the same current follow through all of them back to the supply. So I can't take it as a common. Yes, I can. You see here, I took it as a common. Now, what we come up with? We come up with current is the same, so 1 over C1 plus 1 over C2 plus 1 over C3 will be 1 over C equivalent, as you can see here in this formula. Now, one more issue for the capacitors need to be mentioned here, that, or let me apply this example first. Two capacitances, one of them is 2 microfarad, the second one is 1 microfarad. They are connected in series. Find the equivalent capacitance, repeat for series and for parallel. For series, 1 over C equivalent equal 1 over C1 plus 1 over C2, or we can rearrange it. C equivalent is 1 over C1 plus 1 over C2. Do the math. This is the equivalent. What about the parallel? Parallel, we add them directly, C1 plus C2. Just do the math. One more issue need to be mentioned here for the capacitor is the capacitance itself, how we calculated related to the area and diameter, area of the plates and diameter and width of the plate. Have a look here. The area of the plates is the length, as you can see here, multiplied by the width. This is the area. Okay, depth is the distance between the two plates, as you can see here. The capacitor C equal to epsilon A over D. We know at A and D, but what is epsilon? Epsilon is the dielectric constant. It's related to the material we put it as a dielectric, as an insulator between the two plates. Okay, if we use air or vacuum, then this is called epsilon naught, which is for air. What about for vacuum? This is constant, but epsilon is the vacuum value multiplied by the relative value related to the material used. If it is air, then we multiply just by 1. If it is diamond, if it is mica, polyester, and so on, we have different value for epsilon r. Now let's apply this in example. Now compute the capacitance of a parallel plate capacitor having rectangular plates 10 centimeter by 20 centimeter. He gave me length and width, separated by distance, which is d, 0.1 millimeter, and the dielectric is air. Since it's air, it's 1, it means. Then width by length, I multiply them. You need to convert them into square meter, okay? So multiply by 10 to power minus 2 here and 10 to power minus 2 here to convert into meter square, and rather than centimeter square. Now d in millimeter given, okay, I multiply by 10 to power minus 4 to convert into meter. Make sure to have the same units. Okay. Now epsilon, we have it as a constant, it's given to me. I calculated A, I calculate D, then do the math. This is the capacitor. It's in nanofarad, 10 to power minus 9. Another example to close this part, we want to design a 1 microfarad capacitor. Compute, okay, compute the length required for the rectangular plates, 2 centimeter width, if the dielectric is polyester 3.4 dielectric constant and 15 micrometer thickness. Now he gave me now the capacitor in microfarad. Okay, I know the formula. Now width is given to me in the question. It's 2 centimeter. I converted into meter, 0.02 meter. Diameter is 15 micron. I converted into meter, and epsilon are given in the question. Just substitute. The only unknown here is the length. But see the length, 24.9, around 25 meter. It's long. Can we put capacitor? Its length, the length of the plates is 25 meter? No, definitely, because we want to make the circuit small. So what we should do? What we should do is actually we spiral it, circulate it, make it as cylinder. For that you see the capacitor as cylinder. Now let me go to the second part, which is the inductance. Inductance also passive elements. It's made of wire, coil or wire, or sometimes they call it choke. Okay, as you can see here in these figures. Now they make a wire cylinder, spiral. They rotate it in this way, and when current following through it, it's produce energy. This energy stored in the which is magnetic energy stored in the coil. Okay, definitely they add iron. This is, by the way, back to Faraday. As you know, Faraday say the electromagnetic induction time varying magnetic flux linking coil inductance voltage across the coil. It means when current follow through the wire, it's produce magnetic field. This magnetic field is produced, according to Faraday, magnetic energy which cut the wire and produce again voltage. Okay, it's represented by V equal L di over dt. Now what is the unit? Unit is Henry. Okay, usually it's millihenry, microhenry, small values. Now inductance, as you can see here, it take different shape. It could be toroidal inductor, or could be coil one, or could be inducting with laminas similar to the transformer, as you can see here. It's represented by coil, as you can see here. Current follow through it and voltage across it. Each one of these coil represented by, you can see here, like a ring. Okay, current will follow through it, producing magnetic energy. And the voltage produced opposing the voltage of the which circulate the current through the inductance. It's a passive element, store magnetic energy, okay? And we can represent the voltage. By the way, just to remind you for the capacitor, the main player there in the capacitor is the voltage. We have the voltage usually. So we find the current, which say current I equals C dV over dt. Now here in the inductance, the opposite. The main player is the current, as you can see here. So the voltage will be L di over dt. L is the inductance, okay, of the inductor. And since we have the voltage, we can do cross multiply to find the current in terms of voltage, which will be integration now rather than differentiation. And again, the power is voltage time current. And energy, we substitute the formula of voltage time current, and we substitute the current, the voltage by L di over dt from here, okay? As you can see here, it becomes cancel delta with delta, I, L to be outside, as you can see here. Then integrate I will be I squared over 2, which means energy stored in the magnetic energy stored in the inductance equal 1 over 2 L I squared. Now let's see, we will follow the same discussion for the capacitor here. Also, here you see the current given in this formula. He asked me to find the current for through a 5 Henry inductance, and to plot the voltage, power, storage energy to scale versus time from 0 to 5. You can see also I have here a range from 0 to 2, from 2 to 4, similar to the previous example in the capacitor. And I want to find V, where V is L di over dt. Okay, here I given to me. So differentiate. But first we need to represent this figure by a formula. We represent it and then we differentiate with respect to time multiplied by L to give you the voltage, as you can see here in this formula. After that, current multiplied by voltage, what it give me? You will say it give power, yeah, correct? Now, power, we found the formula which say that energy, which is integration of power, give me as a final formula is 1 over 2 L I squared. We have I, yes. So square it, multiply by L and divide by 2, it gives you the energy. Now, inductor current with constant applied voltage, when the voltage is DC, similar to this one, you see here, constant, 10 volt, as you can see here, 10 volt. Then I will be 1 over L integration V dt. So just from 0 to t, it will give you 5t. Okay? Now 5t, t, if it is going to infinity, does this mean that the current will be infinity? No, definitely. Okay? Have a look here. The relationship happen for the voltage and inductance. It's worth to be mentioned here. This is the nature. Okay? When we apply voltage and circulate current in the inductance, what will happen? At the beginning, the voltage behave as a short circuit and current increase slowly until it reaches the maximum voltage and the current will be 0. No more current will flow through the capacitor because it's fully charged. The opposite happen, but for the current. The same happens, but for the voltage. The inductance, when we apply voltage across it, at the beginning it behave as open circuit, okay? And current start increase gradually until it reaches the maximum. The voltage go to 0 and it behave as a wire, short circuit wire. Okay. Now see this example. The voltage across 150 microhenry inductance is as shown figure. The initial current at its 0 and find the plot the current. Have a look. Voltage now given to me. You remember what we say? V equal L di over dt. So cross multiply and rearrange, you will find that I equal 1 over L integration dV over dV dt. Okay? Definitely this is the initial condition we need to consider. Now for this example, we have from 0 to 2, as you can see here, from 2 to 4, and from 4 to 5. Okay? From 0 to 2, this line, as you can see here, we need to find the formula. We found it to be 7.5 10 to power 6. Please try to find it by steps. It means you have 2 points, find the equation, say y minus y1 equal m between two brackets x minus x1, and substitute the values, rearrange the equation to come up with a formula. So I got it here, as you can see, 7.5 10 to the power 6t. Then when we integrate, t will be t squared over 2, as you can see here. And L is given to the question, which is 150 micro from 0 to t. Then we find the formula. This is the formula. We repeat the same thing, but here have a look. The voltage is 0. Okay, so the part we integrate is 0. So what is left? What is left, as we mentioned before, the previous state. Previous state, it means this equation will be applied. So just substitute here t by this value, which is 2 microsecond. It gives me 0.1 ampere. The third part, which is from 4 to 5 microsecond, the previous state is 0.1 already. I know it. Then integrate from 4 to t. The formula for this line, how much? It's minus 15. I substitute minus 15 and I integrate. Then this is the final shape or the final equation. Now connected capacitance and inductances in series and parallel. In series, we use the same Kirchhoff voltage law. Voltage across all inductances here equal to the total voltage here. Okay, as you can see here, V1 plus V2 plus V3 equal V total. And since the current is the same, they are series, then take di over dt as a common, then L1 plus L2 plus L3 equal L equivalent. Now this means that connecting inductances in series is similar to connecting resistances in series. What about parallel connection? We use Kirchhoff current law, similar to the discussion for capacitors. 1 over L integration GV V dt. And since the voltage across each one of these inductances is the same, we can take it as a common, as you can see here, as a common. Then this lead to 1 over L equivalent equal 1 over L1 plus 1 over L2 plus 1 over 3 and so on. Let's take example. The current through 10 millihenry inductance is 0.1 cosine 10 to the power 4t. Find the voltage and the storage energy as a function of time. Assume the reference for Vt and It have been passive configuration. Angle in radians. Have a look. If I want to, this is V. L di over dt. This is the formula. I given to me, so differentiate. This is cosine. Differentiation of cosine is minus sine. Okay. Then we come up here with the formula. What about omega? Which is the energy. Energy 1 over 2 Li square. Do we have I? Yes, we have. It's given the question. Just square it and simplify. This is what we come up with in joule. Another example. The voltage across 150 micro Henry inductance is shown in figure. Okay. The initial, here the voltage given. The initial current is 0. Find and plot the current. Okay, the current. Now I is 1 over L integration of voltage. Okay, L is given to me. I substitute directly. So what is left? Integrating V. I need to find the formula for this part. This part is already known, which is 0, and this part is already known, which is minus 15. Again, from 0 to 2, from 2 to 4, from 4 to 5, integrate to come up with the answer. Please follow the steps similar to the previous example in previous slides. Now see, when we have more than one inductance connected together, how we find the equivalent? We start from the last, or this may far point from the source. I mean, here is my source. Okay, then this is the last or far inductances from my source. They are connected in series. Then 2 plus 3 equal 5. And the results is connected with this one in parallel. So L equivalent will be 5 by 5 over 5 plus 5. We go to 0.5. The results will be connected with 1 in series, as you can see here. It's like dealing with resistances. The same principle apply here. Now, usually we put metallic iron inside the coil to increase the magnetic energy, and it's preferable to that this metal is contain sheet lamination to reduce the effect of what we call it eddy current losses. Eddy current losses, it happen because of the when we have iron and magnetic flux surrounding this iron, cutting this iron, it's to produce current and voltage in this iron. This current called eddy current. It's losses to produce heat. Okay? For that, when we make it a laminate to reduce the effect of eddy current losses. Now, last point here is the mutual inductance. You know, in the circuit, we have more than one inductance. Connecting inductances close to each other, each one of them, the magnetic field will affect the other one. So as example here, this inductance 1, and this is inductance 2. And this solid point here and here represent the direction of the field, okay? Now the first one, voltage V1 and I1 apply across it, and V2 and I2 across the second one. If we want to find V1, we know that the formula say L1 di1 over dt. That's fine. But what we add also? We add the effect of the other inductance, L2. We add it by multiply M di2 over dt. It means there is another inductance close to my inductance, which is L1, affecting this inductance. And the current following the next inductance, which is I2, will affect. M is the mutual inductance. It means for each inductance, there is self-inductance, which is L, and there is a mutual inductance, which is M. Okay, both of them in Henry. The same thing could be applied here for V2. V2 equal ML2 di2 over dt, but we add M di1 over dt, which means the effect of the mutual inductance from L1 on L2. Now, if the solid point in the opposite direction, then we have subtract. You see here, minus, minus. Let me stop here, and more problems to be solved in the practice exercise in the tutorial. Hope to see you there. Please try to follow the examples discussed in this module and try to solve it by yourself to make sure that you understand the procedure. Thank you. See you in the next module.